So in this class, I will introduce dynamic networks. Until now, we have mostly worked with static networks, so networks in which we have a set of nodes and a set of edges. And these nodes and edges are fixed once and for all. But in fact, most real-world networks are dynamic. So if you think about friendship in Facebook, for instance, you see that all the time there are people joining the network or leaving the network. People are becoming friends or unfriending, so you have relations which are created and removed all the time. If you think about a Twitter mention network, it will be something similar. So every time someone is posting a tweet with a mention, you can see it as an interaction between two people, but these interactions are punctual. They happen all the time and between different individuals, and it's only when you look at the whole picture that you will see a network which is that you can study with the tools we have seen until now. So in both cases, we have something which can be modeled as a temporal or dynamic networks. Usually, so you have to, what we do with Twitter, for instance, is to aggregate. So until now, we will have aggregated over the whole period that we want to study and created a single static network with this data. But what we can do also is, for instance, to aggregate every year or every month or every day, and we will have, in this case, a sequence of networks, for instance. If you think about other types of networks, like the World Wide Web, you also see that there are new web pages created every day and new hypertext links between them. And even on something like an urban network, in which you have, for instance, edges will be roads. The evolution of the network is much slower, obviously, but you still have all the times, for instance, walks on the streets that will close some roads to circulation, or you might also have some traffic jam on the roads, and if you want to use this network, for instance, to compute shortest paths between locations to help users move around in the city, then you need to consider that sometimes some of these connections are closed or open. So you see that many networks can be seen as evolving networks and can be studied as such. So most real-world networks are in fact dynamic, and they are dynamic because nodes can appear and disappear, edge can appear and disappear, and also the nature of relation can change. So nature of relation can be, for instance, I don't know, someone who can change from a friendship relation to a family relation, if someone gets married, for instance, or friendship can move to a business relation, for instance, or the opposite. And or more simply, you can have weights on the edges, and these weights can evolve also during a long time. So you see that not only the structure of the network can change, but also the information on the nodes, on the edges, they can also evolve with time. But this is something we will see more in details later. In this class, I will mostly focus on the evolution really in terms of nodes and edges. So the question is how to represent those changes, how to manipulate dynamic networks. We will see that sometimes we can use tools we have already learned, but sometimes we need to redefine. The first way to differentiate dynamic networks is when we are confronted to a real phenomenon that we want to analyze, is to understand if they are composed of relations or of interactions. So intuitively, we understand the difference between these two things. Relation can be, for instance, a friendship relation, or being colleague with someone, being of the same family of someone. This will be relations. While interaction are something which are happening between individuals, but which are more maybe occasional, and usually not lasting a long time. But we also see that there is a relation between these two things, between relation and interactions. Often, for instance, interaction will occur between people having a relation, or relations can form when people start to have frequent interaction, for instance. So other example of interaction can be emails, text message, or co-authoring a papers. This can be interpreted as interactions. We see that we have to be careful that interaction does not necessarily mean instantaneous, because if you think of a phone call, for instance, it's clearly an interaction, but still it has a duration. So, and some relations sometimes can be understood as something very, very short, like for instance, being collaborator on a project can be understood as a relation, but it's not necessarily very long term. We know that it will have an end after some time. So the way to interpret when we are confronted with something as a relation or an interaction is helpful to give us a first idea of how we will model it, but not necessarily means that we can transpose this into a network formalism, because we are not certain if something is always a relation or an interaction. So when we want to transpose this observed real-world phenomenon into a dynamic network, there are several ways to model it. So, for instance, we can see that an edge presence can be punctual or have a duration. Okay, so you can represent it as, for instance, saying that this edge appeared at time t1 and again at time t10, for instance. But there is no duration. On the contrary, you can assign rather an interval to the edge and say that this edge exists from t1 to t10. Okay, and in this case, so you will represent this as an interval. The node presence can be unspecified, punctual, or continuous. So there is punctual and with duration as before, but there is also in some cases the presence is unspecified. So, for instance, if you observe, I don't know, phone calls between individuals, you know when the edges exist, but we don't know when the node exists, because we don't have information about the individuals themselves. So in this case, the presence of the node is unspecified. On the contrary, for instance, if you study the network of friendship on Facebook, well, you know, for instance, if an account exists or not. So in this case, you will represent your node as a continuous interval presence, for instance. If time is continuous, it can be bounded of a period of analysis or unbounded. So again, for instance, if I want to study from Facebook from the beginning to now, then it's bounded. We know the beginning and we know the end. But sometimes we can maybe just have a bunch of interaction without knowing when is the beginning and when is the end exactly. If nodes have attributes, they can be constant or time dependent, as I explained before, and same thing for the edges. There is also, I need to say a few words about vocabulary, because in this class the title is Dynamic Networks, but I could also use dynamic graphs or longitudinal networks, evolving graphs. All these terms are used in the literature because it's still a quite recent topics. So everyone does not agree yet on which word to use, and in particular which word represent exactly which formalism. So the exceptions maybe are with some specific terms like this one. So link stream and stream graph have been proposed by some authors in particular. In the same idea, you have temporal networks, contact sequences, and interval graphs, which are 3 types of network precisely defined in this paper. And you have time-varying graphs also proposed in this paper. So when you use a name like temporal networks, if you can really anchor it in this paper if you really want to use their formalism. Or if you don't do it, well, we will maybe assume that you will introduce your own definition of what is, of how you represent the dynamic network. So let's go back to the problem. We have some data process observed of interaction between individuals in real life, in social media, or whatever, or even any other type of data. And we want to represent this as a dynamic network. So I will distinguish three main ways of representing it, which I think are representative of what is possible. The first one is maybe the most simple to understand and to analyze, and is to transform it in a sequence of snapshots. So basically each snapshot is a static graph, and you have one static graph for a period. So for instance here you have three snapshots, t1, t+1, t+2, and they can correspond, each of them correspond to 1 hour or 1 day, 1 week, 1 month, whatever. The second types of representation is like this one. So you see that nodes, the one in the middle, the horizontal line corresponds to nodes, and so time is represented on the horizontal axis. And you see that you have an interaction between two nodes at one particular time. So some interaction can happen at the exact same time, usually because we have a given frequency of observation. Well, I don't know, we observe every second or every minute or every hour. So we might have several interactions occurring at exact same time. But nonetheless, you see that the network at each time is very, very sparse. And finally, on the right, you have a representation in terms of intervals. So how to understand it? For instance, this, if you can see, maybe not this one is easier for you to see. So this represents an interaction between A and B starting at 0 and lasting until 4. So this is an interval, representation as an interval, and this connection, this interaction, or this relation exists between these two nodes for this period. Obviously, you can move from one of these representations to the other, either from the original data or one from the other. So for instance, if I take this one, the one in the middle, and I split somewhere, I can aggregate all the interaction occurring during a period and aggregate this into a static graph that will be used as a snapshot. Another possibility is if I have this this network of long-lasting relations, then I can take one particular time, like this, for instance at 1, and consider every edge and node active at that time as a snapshot, so as a static graph. So let's take a concrete example with this dataset on the left that you can see, which is extracted from a real dataset from the Sociopattern project, in which the idea is to give some electronic tags to people that they have to wear, and every time they are face to face at less than 2 meters from each other, they are considered in interaction. And the idea is to give those tags to a bunch of people, for instance, a whole high school or primary school or in a hospital. So they have done this kind of experiments in which they give these tags to all the people in a particular setting, and they record every 20 seconds for technical reasons. They collect every 20 seconds all the active relation between individuals. And this is what you have on the left. So the first column corresponds to a timestamp. So this corresponds to one particular second in time. And these are, U and V are two nodes that are connected at that time. But this kind of dataset, this representation of temporal network is very common, and if you get a dataset on the internet, often it will be in this format. So, for instance, the Enron dataset, the famous dataset of email exchange between employees, also is in this format. And what is interesting is that the exact same data can be analyzed and represented into different formalism. So first, as snapshot, you see that this data, I can consider it as all the lines corresponding to the same timestamp can be grouped into one snapshot, for instance. I could either adopt the link stream representation, in which each line is an interaction that I will represent at this particular time, and the second one will be another. So this is not obviously the network representing these interactions, but just for you to get the idea. And the final one will be to consider that if an interaction which is observed on one timestamp is still active in the next timestamp, then it's that the interaction actually lasted between these two times. And this makes sense because, for instance, we know that we observe the interaction only every 20 seconds for technical reasons, as I said. And so, for instance, this green, this edge highlighted in green is active in the first period. 20 seconds later, it's still active, and 20 seconds later, it's still active. So you can consider that this relation is actually lasting for a period. So you see that there is not always an obvious choice of representation for a particular dataset. So let's now consider that we have chosen a dynamic network representation, and that we made the data collection process, and we have our dataset, our modeled as a dynamic network. So how to analyze it? First, it depends on the way we have chosen to model it. So if we have only a few snapshots, so few being maybe 2, 3, 4, maybe until 5, but not much more than that. The other case will be if we have something I would call the slowly evolving network. And the last case is having what I would call a degenerate or unstable temporal network. So the first case, if we have a few snapshots, well, it's quite simple. We have seen tools to analyze static networks, so we can apply those tools on the 3 networks and then study kind of manually the difference between these networks. So you have an example visually here of a network evolving in 3 steps, and we can see that the network is being more is growing, more nodes, more edges. Then we can study the density, for instance, or the position of a particular node. Does it stay in the center, or does it get integrated in some part of the graph, whatever. So clearly in this situation, you see that we cannot visualize the network as a movie because we don't have enough details for that. We just have a few networks which are quite different but still retain most of well, you can still recognize some part of the first network on the first step and on the second step, in the second step. So there is not much to say about this representation. You can just apply the classic tools, and that's actually what has been done in many research until maybe 10 years ago. That was basically the only way to do. There is another type, completely different, of network to analyze, is when we have something which is slowly evolving. So It's the situation in which you could visualize your network as a video, for instance, because things are moving, changing one after the other. So for instance, you see one edge which appears, another edge which disappears, but 99.99% of the network stays the same between one snapshot, one time, and the next, basically. Another way to understand this type of network is that it is well defined at any t. So if you take, so let's say that your network is going from t0 to t1000. If you take 327 and you look at the state of all the nodes and edges that exist at that time, you have a legitimate static network that you can study. So there is no formal distinction with previous case in which you had only 3 or 4 snapshots. So it's just that you have a higher observation frequency, and thus you can really analyze what's going on in your network in more details. So this is an example of such a network. So as I said, you can observe it as a video. As a movie. The problem when visualizing it, as you can see in this example, is where to put nodes, because things are changing. So it's actually quite difficult to do this type of movies and still having something that can be understood. So when you have this type of network, you can study in more details. So for instance, you can look at the evolution of some global graph properties. Like in this paper, for instance, the authors studied the average out degree of some dataset, and they have observed, for instance, that it was growing with time. Or on the right, they have studied the diameter of real networks also evolving with time, and they have observed that there is a shrinking diameter. So a long time in these real networks, the diameter is actually decreasing, which is an interesting phenomenon because you have more. They have observed that there are more nodes and more edges, and nevertheless the diameter is decreasing. So you can make this type of analysis, or you can also for instance, study the evolution of the centralities of some particular nodes. For instance, in this case, for consumer or producers, they evaluate the evolution of the closeness. And that's a process you can do to understand how things change with time at the level of individual nodes. And since you have now enough data, you can also use more advanced tools like time series analysis, which is a whole field of research, right? Time series. And so time series are very often used to model things like stock market prices or temperatures in a particular location. So you have this time series of value, and you can create time series corresponding to the density of your network, the centrality of a particular node, and then study, for instance, things like periodic patterns. I don't know, a node that will be very active every Christmas, for instance, if you have some data over several years, or detection of anomalies. So I don't know if you're looking at the internet and the request to some servers on the internet. You can have some nodes who makes attacks, for instance, and you can detect this using time series analysis. You can have identification of global trends, evaluation of autocorrelation, prediction of future values is also a very popular field of research. So if you have this temporal evolution of values, you can try, well, maybe to predict what is, for instance, how the number of users or the density of an online social network behaves. The third type of dynamic networks you can be confronted to is the one in which the temporal network is unstable or degenerate. So the way to understand it is that now if you look at the network at a particular point in time, particular t, the network is not meaningful. So a typical example would be emails. So let's say that you have collected a lot of email exchange between thousands of individuals, a world company or a world university. And you have the particular second at which each email has been sent. So now if you check a particular second in time, so I don't know, today at exactly 2 p.m., and you check all the edges at that particular moment in time, you have only the people who have sent an email at this exact second, and obviously this is not a meaningful network. So in that case, you need to use some specific tools to analyze the network. So this is the example I've illustrated before, especially on the bottom, and on the top you will have more some things like cell phones, but still you see that in this network they are not really relation, because if you check this time, for instance at time 4, there is nothing active in the network. So it means that your network is changing very quickly. So you probably need some specific tools to study such a network. So one solution, obviously, is to transform it into a more stable network using aggregation or sliding windows. But the problem is that you will lose some information. You lose the order of everything which happened in your window of aggregation. And also, the network you will create will be completely different according to the aggregation windows that you have chosen. So if you choose a window, for instance, in my example of the emails, if you choose a window of 1 hour, for instance, your network will still be very unstable. If you take a duration of 1 week, it will probably be quite stable, and if you take 1 year, then it will be probably very stable. So when you choose this window size, you fix once and for all some time scale that will affect your analysis. So that's why new theoretical tools have been developed to deal with such networks. So these 3 papers in particular I presented, they really introduce how to deal with those networks, and you can report to them if you want more details. In this class, I will talk about network properties in stream graphs. So stream graphs are presented in this paper. You see it's a relatively recent paper, in which they try to redefine many of the classic definition on static networks that we have already introduced, like centralities and density, these kind of things. But they introduce them for unstable networks that they call stream graphs. Well, their formalism is adapted to any kind of network, so stable or unstable. So they define a stream graph by T, V, W, and E, with T being a set of possible times. So that's why they can adapt to any kind of networks, because they say that T are times that can be intervals or just discrete times. V is a set of nodes as usual. W is the vertices presence time. So you can, in some situation, you can not have anything, and in this case we call it a link stream. But we won't enter and we won't go into details in this class. And finally, E is defined as the edge presence time. Right, so you will have a pair of nodes and a possible time, which is discrete or time interval. We also introduce some new notions between entities and time. In particular, the capital VT corresponds to all the nodes active at a particular time. ET corresponds to edges at time t. And thus GT is a snapshot. So it's a snapshot composed of V, T, and ET. Then we define a node time as lowercase vt. It means that if you have vt exist if node v is present at time t. And similarly, there is an edge time. The edge time means that the edge uv exists at time t. And you have also capital T-U, which is all the times represent all the times of node u. And TUV corresponds to all the times at which UV is present. Okay. So now that we have introduced the basic notions of stream graphs, we can introduce new notion, and the first one is node presence and edge presence. So this is quite simple. It's just that since nodes and edges are not present all the time, we want to quantify how much they are active, how long are they active in the graph. So it's very simple. The edge presence, for instance, consists in counting the duration, total duration during which the edge is present, and to divide by the total duration of the stream graph. And same thing for node. We count how much they are present, are active in the graph, and what is total duration of the graph. And we get the fraction during which they are present, so a node presence. So typically this value is between 0 and 1. 1 means that the node or edge is present all the time. So having introduced this new notion, we can redefine static notions on stream graphs. And the idea, the principle of this is to have a definition such that if the nodes and edges are present all the time, then the score computed with the redefined notion on stream graphs will be exactly the same as on a static graph. If you take a static graph and you extend it for a period of time, you apply the notion we define on this stream graph, and you should get the same notion as on the original static graph. So the first notion we will redefine is simply n, so the number of nodes. If you remember, on a static graph, if we have, like in the graph on the bottom, you have A, B, and C. So in a static graph, we will say that there are 3 nodes. But in a stream graph, actually, what we want to compute is the quantity of nodes. So how much nodes there are in the graph in average. And so the way to do it is very simple. It's just to compute the sum for all the nodes of their NV, so what we have just defined before, the presence time of nodes. So we compute their presence time. So you have an example on the bottom. For instance, the one on the right. You see that A is present during a period of 1, from 0 to 1, period 1. You see that node B is present all the time, so from 0 to 3, so period of duration 3. And C is present during a period of duration 2. Okay? So if you sum this, it's 1 plus 3 plus 2, it's 6. And you take this total duration of 6, and you divide it by the duration of the network, which here is 3, and you get 2. So the quantity of nodes in this graph is actually 2. You can do the same computation on the left, and you see that in this case, again, you have 1, 3, 1, 1, and again, we have 6 that we divide by 3, the total duration of the graph, and we get a value of 2. We can do the same thing with edges, and again, very simple. We just compute the sum of what we have defined as the presence time of edges. And if we take these networks on the bottom, you see that the total duration is 1, which is very simple to see on the right, because you see that there is one edge that exists from 0 to 1, and one edge that exists from 1 to 3. So obviously, in average, there is one edge. It's the same thing on the left. You have an edge of duration 1, an edge of duration 1, another one of duration 1. So it's a total of 3 that you divide by the total duration of the graph, which is 3, and you get a total duration of 1. So from these notions, we can move to something a little bit more complex, which is the edge domain, or the maximal number of edges that we could have in the graph. And actually, we can see that there are several ways to define such a maximum number of edges. So one of them will be to ignore node duration and just to take the number of nodes defined as in a static network squared, if we consider that we can have self-loops. I don't go into details here, but the idea is here that if you have A, B, and C, and you ignore the fact that they are not present all the time, and you just consider that there could be at max a number of edges, which will be 3 squared. So 9. Another possibility will be to take into account the total duration, the presence time of nodes. So we know that if nodes are not present all the time, when they are not present, they cannot have an edge. So you can compute, in this case, the maximal number of edges that could exist by taking n squared. And the final definition, which is actually the one adopted in the paper of Latapi et al. That was on which these definitions are based, is to take into account the copresence of edges. So the idea is that if two nodes are present but not at the same time, then they cannot be linked. So you will only count for the edges the time during which the nodes are present together. And you consider that an edge can exist between two nodes only if they are present together in the graph, which makes sense, obviously. So having defined this, we can now define the density. And what is interesting now is that we can reuse the exact same definition of density as for static graphs by saying that the density is L divided by L max. So the number of edges, the quantity, the presence of edges, divided by the maximal possible presence of edges. And with this definition, you can see that in these two graphs that have the same number of nodes and the same number of edges, they have actually a different density. It's 1 on the right, because every time two nodes are present together, they are connected. So A and B A is present only from 0 to 1, and during this whole period it is connected to all the other nodes, because C is not present at that time. The presence is represented by those dots, dotted line. And from 1 to 3, we see that B and C are present and they are connected, but A is not here. So every edge which is possible, because two nodes are present at the same time, every edge which is possible exists. So the density is 1. It's actually could be considered as a complete graph. While on the left you have an example in which some edges that could be possible, so between A and C, it's possible to have an edge from 0 to 1, but there is no edge. So this means that the density is not 1 in this situation, and actually you can check that the density is 0.75 in this case. Another element we can redefine is the notion of clusters and substreams. So a cluster in a static graph was a set of nodes. A community was a set of nodes. But in a dynamic network, actually what we want to define is now a set of node time. So we want to define a set of node time, and from this we can define a substream. Like before we had defined subgraphs. So a substream will be a stream which is defined by a cluster composed of node time. So let's take an example. You see so this is on the left, you have the drawing of a stream graph, and in blue you have what represents a cluster. And you see that this cluster is arbitrary. So it starts, for instance, the blue line of A start at 1, while actually A is present from 0 to the end of the stream. So we just decided, just for the sake of example, to have a cluster which is composed of A from 1 to 4, and from A from 5 to 8, then from B to 5, of B from 5 to 9, and from C and of C from 3 to 8. So we have decided to take this cluster, and you see that it's not composed of A and B, but of A from 1 to 4, and so on and so forth. So it's really a set of node time. And on the right, you have the corresponding substream. And obviously, you see that the nodes are represented with dots during a period corresponding to the blue lines. And edges exist between, we have kept only the edges between the nodes that do exist. So for instance, if you look at the edge between A and C, you can observe that in the original graph, this edge was starting at time 2, while in the new one, it's starting at 3, because C is not present in the graph from 2 to 3. Another notion which is very interesting to study on stream graphs is the notion of path and distances. So we need to redefine the notion of path, and we do it like so. So we want the path to go from a node time, so a node time node x at time alpha, to another node time, for instance node y at time omega. So this means, for instance, in the figure which is here, the starting node time and ending node time are represented as red crosses. So we want to go from this node time to this node time. And we will define this path as a sequence of hops between node times. So for instance, the first one here is starting from a time t0 from node x and moving to node v0. So this means that there needs to be an edge between x and v0 which exists at time t0. And this t0 must be greater or equal than alpha. And then we can move to another time, later time, from a node v0 to a node v1, and so on and so forth, until reaching a last hop between node tk, at a time tk, from the node vk to the destination node y, okay, the destination. So this defines a sequence of hops, exactly like a normal path in a static graph, but with the temporal component. We will say that this path starts at t0, so it starts at the first hop. It arrives at tk, so at the last hop, so which is not necessarily the same as the node time we have chosen. It has a length k plus 1, so length is a number of hops, exactly like in static graphs, and a duration, which is the difference between the arrival and the start. So if we take the example here on the same stream graph, these correspond to two different paths. And you see that so there is a first hop here, a second hop there, and a third here. So this path has a length of 3. 1, 2, 3. while this one has a length of 1, 2, 3, 4. So you see that they both start from the same node time and arrive at the same node time, but they do not have the same length. And they also have a duration which is different. So this one has a duration of 3, and this one has a duration of 5.5, because it arrives at 7.5, I think, here. And and this one starts at 2, this one starts at 2 also, and this one arrives at 5, and this one arrives at 7.5. So now we see that it's a little bit more complex to define a shortest path, because there is, so again, the shortest path is just the path with the minimal length. But we can also define a fastest path, which is the path of minimal duration, and the foremost path, which is the path arriving first. So it's very important. So depending on what you're interested in, you might be interested to reach the node as soon as possible, like in this situation. So the foremost path. If you want, for instance, to, I don't know, send an information to someone, you might be interested in the foremost path. But if there is a cost, for instance, associated to moving from node to node, then you might be interested in minimizing this cost, and so to search for the shortest path. Or you might be interested to look at the fastest path if the cost is more, for instance, proportional to the duration. This combination can be combined also, and actually when we are searching for path in a stream graphs, in a dynamic graph, we tend to search for fastest shortest path, so the path of minimum duration among those of minimal length, or you might search for the shortest fastest path, which is the path of minimal length among those of minimal duration. Just something I forgot to say, that it's really important to look at the order of edges when you're searching for path in dynamic graphs, and this can be illustrated with an example like this one. So where there is an edge between A and B over this period, and there is an edge between A and C over this period, and we see that if we look at the information that can spread from node to node, so information or even a virus or something like this, you see that it's very important to consider the order, because this means that something can spread from B, for instance, a virus can spread from B to A if they are in contact here, and it can spread from A to C. So something can spread from B to C. But knowing the order of the interactions, it's not possible that something go from C to B, considering this interaction and this interaction. So considering only these two interactions, it's not possible that something go from C to B. But if we aggregate the network, we see that we don't know, we forget about this order, and so it seems possible that something spread from B to C and from C to B. But taking into account the order of interactions add this constraint. A final notion we will introduce is the notion of connected components. So actually you can check for more details in the original paper. Here I will just introduce the simplest notion, which consists in searching for sets of node pairs for which there is a path between them, not looking at time constraint. So you see that, for instance, B, so each color corresponds to a weakly connected component, and we define this weakly connected component as being able to reach ignoring the order of time. Otherwise, it's much more complicated when you want to define connected component on graphs considering time. And in real graphs, actually, it's very difficult to find strong connected component. But here, these weakly connected components are very much easier to understand. And you see that a same node, for instance node T, can belong to one connected component for a period and to another connected component during another period. Another notion I wanted to introduce is the notion of random models. So this is coming from mainly from another paper, and I will of course just introduce the topic and not go into details, but you can check more details looking at this paper and others on the topic. So I already introduced why random networks were important, and in particular it's important when we want to compare a network to a randomized version of it to compute some clustering coefficient. Well, when we compute a clustering coefficient, associativity, modularity on a network, we need to compare to a random network to see if the values are large or not, or small, or expected by chance, or whatever. So in a static graph, we have introduced the Adoshreni model, the configuration model, and we don't see much other things that we can easily keep other than just the number of edges, or the number of edges and the degree of nodes. In dynamic networks, there are much more possibilities. So just to show you some examples, in the paper I just mentioned, they grouped method for random network, creating random dynamic networks in 4 categories. So they use a representation as snapshots, but it can be understood as other representation too. So the first way to shuffle a random network composed of snapshot is to do snapshot shuffling. So it's very simple. You take each graph independently and you shuffle it using, for instance, Adoshreni or the configuration model or your favorite randomization. So you see that this one becomes this one, the green one becomes the green one, and so on and so forth. The second category is sequence shuffling. So in sequence shuffling, this time you want to keep what is happening in each snapshot, but you want to randomize only the sequence in which things are happening. So you keep snapshots and you shuffle the order. So right, it was orange, green, purple and blue, and it becomes green, blue, orange and purple. So using this randomization, you will keep many properties of what's happening in the snapshot. So for instance, you keep the average degree along time, you keep the number of edges, average number of edges, and so on and so forth, but you randomized the order in which they are occurring. Another type of randomization is link shuffling. So in link shuffling, the idea is to keep what's happening for a particular edge. So in this case, you see that there was the edge between node 1 and node 2, which had interaction represented in purple here. So the interaction between nodes 1 and 2 was an interaction during the, second step, and then during step 3, 4, 5, and then two interaction at that time, and so on and so forth. And for the blue, only 2 interactions at time 2 and 3, 4, 5, 6, and 7, 2 and 7. And the idea is to just shuffle the edges on which this occurs. And shuffling without limitation, it means that, for instance, before the shuffling, there was an edge between 1 and, sorry, I need to find it. So there is, where is the difference? 2 and 4, 2 and 3. Yes, so there was an edge between 2 and 3, but after the shuffling, there is no edge between 2 and 3. And on the contrary, there was no edge between 4 and 3, and now there is 1. Okay, and actually this edge between 4 and 3 is a copy and paste of interaction that before occurred between 1 and 3. So basically, you take an edge between in the beginning, you memorize the occurrences of interaction for this pair of nodes, and you shift it to another pair of nodes. So what was before the interaction between 1 and 3 becomes interaction between 3 and 4. Okay, so that's why it's blue here and blue here. So we have kept exactly the same number of interactions. We have kept the number of interaction by pair of node, but we have shuffled the pair of node. So the cumulative graph is different. And the last category is timeline shuffling. So in timeline shuffling, what we do is to this time keep the cumulative graph. So we will keep the same interaction are possible in the random graph only between the same pairs of nodes as in the original graph. But this time we completely shuffle the interactions. So there were 4 interactions on this edge in the beginning, and after shuffling there are still these 4 interactions, but we completely randomly distributed them among time and edges. So we only kept the number of interactions and the possible edges of these interactions. So this is just to give you a sense of all the possibilities of random graphs that exist. And actually, so in the paper I introduced other methods, so like local time shuffling and weight constraint time shuffling, so you can check these examples. And in the paper they even define some categorization like this of the relations between all these different types of shuffling. So as you can see, it's quite more complicated than for static networks, but the idea is that you can choose a randomization which corresponds to your need. So if you want to keep the aggregated graph, but you don't care about what is happening in each snapshot, then you can adopt one type of randomization and another one if you need. Finally, I would like to conclude with a topic which is dynamic community detection. So I will just say a few words about that. You can also check in the experiments in the going further section. I propose some example of working with dynamic community detection. The idea is that we have seen community detection on static graphs, and a community detection on a dynamic network is quite similar, but instead of searching sets of nodes, we are searching set of node time, which means that a node can belong to one community during a period and to a different community at another period, without actually having overlaps, because it's just that they belong to different communities during different time. So I already shown this movie, but actually you can see that it's a visualization of dynamic communities represented by colors, and you see that there are questions such as every time you have a modification of the network, how to update the communities to match this evolution. So you could think that maybe it's just a simple problem. You just have to iterate community detection on each snapshot, if you have snapshot, for instance. So you could apply the Louvain algorithm at every step, match somehow the result using some intersection. So you check, for instance, the communities with the most nodes in common and say that they are the same, and that's it. Your problem is solved. But the fact is that in reality, it's a little bit more complicated than that, for several reasons. One is the question of community events, so growth, contraction, and more importantly, merge and split. So you can have communities that merge and split, and you would like to be able to detect these things. There is another topic I haven't introduced here, which is the smoothness. So you want to have solutions which are smooth. It means that there is not too many changes in communities along time, because if it's changed all the time, you don't really know, you cannot really interpret what you obtained. But yeah, I won't go into details. And finally, you have the question of the identity of communities, which is a topic that I think is quite interesting. If you imagine that you have, so let's start with, so what is the ship of Theseus? Is actually a paradox which was introduced in very old time, because it was introduced by Plutarch in the 1st century. And the paradox goes like this. So Theseus was a famous hero of the Greek, and he went to fight the Minotaur, and then he come back with a ship, and this ship was very famous. So because it was famous, it was kept in the harbor by the Greeks for a very long time. But it was in wood, so the boat started to deteriorate. And to keep it, to conserve it, the Greeks started to replace parts of the boat with other parts of the boat, with new parts in wood. And they have done this for years and years, replacing parts and parts. And after some times, what happened is that actually none of the original part of the boat were still present in what is still called the ship of Theseus. So you have this ship which has none of the part which went to fight the Minotaur with Theseus, but still it's in the harbor and is known as the ship of Theseus. But then where the problem becomes interesting is that if you imagine that someone has kept all the original parts, and clean them and build a new ship with these parts. So this new ship is exactly identical to the original ship of Theseus. And actually it's composed of all the original parts that went to fight the Minotaur. But it's not the one which is known as the ship of Theseus now. And so actually you can ask this question, which one is the ship of Theseus? So that's a paradox. There is not obviously a right answer. And this is a problem we encounter when we deal with dynamic communities. So if you read this chart, this plot, you see that I represented time on the x-axis, and I represented nodes on the y-axis. And so each node corresponds to, so each horizontal line here corresponds to a node. And we observe that originally the community A exists, composed of these nodes. But then nodes are replaced one after the other by new nodes, until after some times you have the community, which is the community B. But actually, very often, this community is represented with the same color, because there is a continuous evolution from one to the other. And then, if you have a new community which appears here, composed of exactly the same node as the beginning, as A in the beginning, the question is, which one is the same community as A? Is it B or is it C? And well, this is one of the problems that one needs to tackle when working with dynamic communities, is this notion of identity. What is the same community later than before? So, to sum up with dynamic graphs, I wanted to say that currently most practitioners still use the snapshot approaches because it's easier. It's easier because since it's a relatively new topic, there are no widespread framework. Like I presented steam graphs, but they have been introduced only 2 years ago, and they are not still widely known in the community. There is no widespread coding library, so there is not a network X of dynamic networks. So there are several ones like PathPy, T-Network, Tacoma, but every one of them is limited to some applications. And also there are not that many datasets available. There are more and more, and private companies have a lot of datasets of this form available, but not so many of them are shared publicly. Nevertheless, I think it's a very important topic to study because, as I said, most networks we actually analyze are dynamic networks, and dynamic is important. Dynamic is everywhere, and yeah, it's changed everything in many cases, as we have seen with diffusion of information, for instance, and for communities also. For instance, it's very different to study the evolution of something, or just to look at a global view where everything is aggregated. So I encourage you to study this topic if you're interested in network analysis.